Okay, this is called Induced Polarization, Circuit Elements and Fences, and it's a bit of a story of my progression from the end of my graduate career here at MIT and moving into my early employment at Kennecott Exploration in Salt Lake City, where I went after finishing here, along with Charlie Swift, a fellow Madden student, and actually another fellow, Will Frangos, who finished up here and had worked with Bill Brace as an undergraduate. So Kennecott chose to build a very nice research place in Salt Lake City at just about that very propitious time for me. But before we get there, this is an electric circuit that shows in red 4 operational amplifiers. And this is actually from my PhD work, but it's not that calls our attention to this. It's rather the presence of the operational amplifier, number one. And number two, it's that Ted was not only thinking about a lot of different geophysical things, he was attracting enough funding at that time to support an active electronics lab and a technician named Sam, cigar-smoking Sam Hendricks, who kept soldering things together as fast as Ted could take them apart and say, we need to lengthen the time constant, let's use a bigger capacitor, please, Sam. The other story connected here with Ted is the operational amplifier, which was, when it first came out, occupied an entire rack. The Philbrick amplifier was a vacuum tube device, and it had this, it was the first of the very high gain amplifiers that populated Ted's lab. Later, Burr Brown came out with this remarkable innovation that shrunk them all the way down to a 1-inch square cube in an epoxy package, and those sold like hotcakes in the geophysics lab. Those enabled us as amateur electronics experts to design circuits and implement them quickly. So it was a wonderful thing to learn. And another grad school era experience was the search for a Crustal-Scale waveguide. And this was back at that time, the military was interested in getting a secure worldwide communications system by finding a high resistivity waveguide. These would be low data rates, but they would be ultra secure. There was a spin-off. We talk about spin-offs now. I see MIT is big into innovation and generating small companies. Well, here was one way back when in the 60s called Geoscience Inc., founded by Tom Cantwell, another Madden graduate. And he formed a little company just over here about 5 blocks away. And I was a summer employee. And when Ted decided to take a sabbatical, I thought, oh, that's good, I'll take a sabbatical too. And I started doing field work with geoscience. And here is one of the cross sections from the state of New York looking for the high resistivity waveguide. Those are 1-mile dipoles, and we were able to make the measurements because of a synchronous detection system that was developed here, and it used WWV as a timing mechanism to sync the transmitter and the receiver. And at the bottom there you see resistivities as high as 18,000 ohmmeters. Phil Haloff credited Ted with this method of plotting up the data from between dipoles. Probably another myth, huh? Oh, about phase shift. Now let's switch to the Kennecott induced polarization experience. And this is a little bit about phase shift, which for metals exploration were quite small, just on the order of a few degrees max. So for small phase shifts, phase was simply the ratio of quadrature to real components. And because the values are so small, rather than expressing them in degrees, it was natural to express them in radians, or rather in milliradians, which is what you'll see. And we were looking at sensitivities of just a few milleradians to get the noise level down to that at the early days at Kennecott. So one of the experimental things I did was to get a digital tape recorder and take it to the field. These data are taken in eastern Nevada, and we had a system, a full field system out there with this tape recorder mounted in a truck. It was this Kennedy stepping recorder, and we recorded these IP signals. You can see the, on the upper pair, you can see the telluric noise riding on top of the induced polarization square wave. And if you're trying to get the sensitivities down to a few milleradians, you can imagine the havoc this plays. It turns out a fellow came up with a nice technique with digital storage for a high-pass filter, which filtered out all these tellurics. And with the tape recording and playback system at the University of Utah, we could actually see what we were doing in terms of filtering and working with the sets of digital data. Another kind of problem in the field recording is spherics, or little bursts of lightning noise. And there you could take, again, with working with a computer, just do different experiments in terms of removing different kinds of noise. So another problem in the field is the field guys are sitting there and they go to low frequencies. The lower the frequency, the more free of electromagnetic coupling are the data, the better are the data. So the question is, how long do you really want to sit here when it's 5 o'clock in the evening and are the data valid? So how many cycles should one wait? And here's the effect of a high-pass filter on phase, noise, and convergence. This was without processing here. The standard deviation is down here and off scale, and you can see the raw data bouncing around and the running average here. This is the same data set with that high-pass filter applied, and you can see the convergence of the phase, and the scale here is every tick is 10 milleradians. We had noise problems of other kinds. One of them was, as we call them, grounded structures, which covered the class of things that are man-made and runs for some distances and are earthed. And these included not just fences in the Southwest, of which there are plenty, but also power lines. And so we wondered, the crews noticed that they were getting spurious responses when they were setting out their lines. And these were lines with 1,000-foot dipoles, and these things went for several miles across the country. So this is a fairly big operation. Kennecott ran 2 to 3 crews at this time. So it was quite a big expense, tremendous investment in the field prospecting method that was based on it is induced polarization. So here's the basic problem. You have a transmitter here and a receiver over here, and in between is a fence, and you're producing this square wave. And what happens is the fence is distributed for a long distance here along this voltage field put out by the primary transmitter. And so this electrode here is at a different potential than that electrode there. And lo and behold, the current wants to flow along the fence. And as it does that, it flows through the grounds, and you get a phase shift at each of these grounds. You get a secondary field superimposed upon on the primary, and you get these phase shifts. So we did a little equivalent circuit for the fence, went out into and represented these as complex impedances, which in fact they are. This is the voltage in the earth. This is the voltage along the fence. There's also a longitudinal resistance. It turned out, darn it, that Madden also addressed this problem with Tom Cantwell years ago along the Mass Pike when they were making resistivity measurements for work out there. They didn't have the phase shift problem, it was just a resistivity problem, and they did not use this approach, they used an analytical approach. But this measurement approach worked pretty well. We demonstrated the dipole nature of the quadrature electric field at field sites in Arizona, and measuring the impedance of fence stakes by first looking to make sure that the rancher was nowhere in sight, unclipping the fence from the fence post, and turning on the transmitter with an electrode close by, measuring the phase shift of the current between the fence and the ground, and very carefully putting the fence back on the post. And so we were able to make a number of impedance measurements and then put them into the little circuit model and model the direction of the field and the phase shift. This is actually a field data with showing the direction of the field. This is the closest electrode to the fence from our little transmitter dipole, 200-foot dipole. And then this shows, we went out with little orthogonal receivers, maybe 10, 20, 30-foot dipoles, I can't remember, in a field receiver. Measured the phase shift. There's numbers from 22 milliradians, 23 milliradians, 17 milliradians. And you can see that the geometric nature of this induced current flow. And down here is the computed fence model. It gives us a similar kind of dipolar structure. So we had felt pretty happy of having diagnosed the noise problem. So we were able to produce a catalog of interference programs. You know how it goes. Once you get a computer model, you can just generate all this stuff. And so it was actually used to create a catalog that people could use to try and figure out what kind of problem they were in and if a particular anomaly was in fact due to a structure or due to a buried sulfide target. So these are total phase values, and showing here the dependence on resistivity. A 500 ohm meter earth produces a much higher phase response than a 100 ohm meter earth. And of course, there are also problems of when the dipole gets closer, when it gets parallel, et cetera, et cetera. Another problem in the field was natural responses that are not due to mineralized sulfides. And here was one from a carbonaceous siltstone. Phase responses of more than 50 milliradians were measured on a particular site in western Nevada. The laboratory spectra on the samples, here's one here. And this is quite amazing. The fellow in charge of our little exploration outfit said, for heaven's sakes, why don't you run this down? Just go out and drill some holes and get some samples of whatever this is. And so the samples were recovered, and it was diagnosed by the petrographer as a siltstone with a remarkable amount of carbon in it, but which didn't show up in the analytical work. It turned out the visual carbon was much higher than the analytical carbon, and we thought that was because the carbon was coating grains and producing a very high electrical continuity in combination with an unusual pore structure. This is the phase response on a log scale versus the log of frequency, 10 to the minus 2 to 10 to the 3, measured in the laboratory. And this is the unusual response, extremely responsive at the low frequencies, tailing off. And this little electric circuit here is could have been straight out of one of Madden's notebooks. Here's a resistor, and here's this innovative electrical symbol called W for a Warburg impedance, which I think was what Ted used in, I don't know, maybe in Madden and Marshall, who knows, to designate this 1 over square root of frequency dependence of an impedance which is controlled by diffusion of ions at the surface between the sulfide and the surrounding pore water. So lo and behold, we got this thing that seemed to be indicating that the electrical problem in this case, and these things were very responsive. It was, you know, they're about to go out and stake a bunch of ground on this thing. But in fact, it was this thing that Will Frango's called anomalite. The IP response was also tied back to things of economic interest, and this is primarily work by Jerry Van Voris, our supervisor at this little geophysics R&D group. This is weight percent sulfides from 1 to 10 weight percent. And these measurements are bulk samples. We went out with pickaxes and shovels and got big lumps of rock, took them back in the lab, broke them carefully to get the weight percent of mineralization in here. And then I think we used 10-foot dipoles in the pits. This is all out of the Kennecott's porphyry pits to get a measure of the quadrature conductivity, which was finally realized to be the most effective electrical measure of the mass of metallic substance within a quantity of rock. So you see this, these are individual samples here, and here's the same data averaged by site with standard deviations on it. So that was pretty much the culmination of the effort to quantify IP response back in that day. Funny thing happened. The last week ago, I decided, well, I'll just do a dry run of this talk over in the USGS, where I currently work, back in the geophysics group where I worked years ago. So I go over there, and I know a few of the people. They're about my vintage. And so I'm giving this talk, and I said, you know, they're kind of nodding, yeah, that's the way it was, that's the way it was. And then the younger people in the audience are just sitting there, and they're all kind of stunned. I thought, that's odd. I thought, well, at least they're awake. But they looked just amazed at what I was saying. I was quite flattered. And then I realized that they were amazed that they suddenly realized that all this stuff had been invented once. And I thought, oh, I'm on the History Channel. And sure enough, this is the way it was. The last, just two more slides, and this is Charlie Swift's paper in geophysics in 1971, and Charlie did his thesis here on magnetotellurics of the Southwest with the field measurements, and his modeling was using the network analog to make two-dimensional models of magnetotellurics response. And here you see the correspondence. Of course, Ted was very much a proponent of this between the electric field and the voltage of the network, the magnetic field and the current, and the impedance was I mu omega, and the admittance was the out-of-phase conductivity. So that was the analog that was used to model electromagnetic propagation. And so Charlie, the paper I think, recapitulates his effort at magnetotelluric modeling, and then he extended it for what's called Turam, which I think is a Dutch contraction of two-frame, which was the prospecting method of putting out a very large loop of wire, thousands of feet on a side, and then marching out away from one of the legs of the wire and measuring the magnetic field. And so Charlie modeled that with this same method. He realized he could do that, and that was part of the paper. And he handed me the manuscript as he was writing it, and I said, oh, Charlie, there's a really neat thing up at the University of Utah Computer Center. The CalComp people, who made plotters at that time, have just come out with a little package, and this is really great because you can make ellipses with this with this contouring with this CalComp package. So let me run some ellipses for you, and I did. And this is Charlie's computation. Here's a current line source over here. Here's the anomalous magnetic field computed around a conductive body down in the earth and up in the air, and then this would be the line of along the Earth's surface. And here's the total field if you add the primary from the current source and the anomalous field. Things look a little different. So here are the ellipses, and they're getting smaller, and they're closing up, and they're flopping over. And this is the origin of the field lying itself down on the surface as you pass a conductive body that's creating its own little secondary field. And here is essentially the visual component of a tilt meter measurement, which I think has already been mentioned in this session. So that's it. There was a terrific legacy, and it just kept popping up. Once Charlie was going through the files, Kennicott's files, he came down to me with this funny look on his face, and he said, "Well, we've been scooped again." I said, "What do you mean?" He said, "Well, I was looking through the files, and I found this 4-page document, and it's signed by Ted Madden." It turned out Ted had been a consultant for Kennicott a few years ago, and he had, in a few concise pages, had outlined the mathematics for this Turam method. So, alas, that's the end.
I am just going to ask one question, and it is, after all these innovations, you people put Kennicott out of business. Was it they didn't take your advice, or you spent so much money that they couldn't mine copper anymore?
Well, yeah, that's an interesting question. The real art of working in the applied earth sciences is finding an outfit that has enough sustained cash flow for a long enough time that you can continue to do applied research. So it was as they say, the price of the commodity did not warrant the continued sustenance of such a group.
And you're not going to put USGS out of business, are you?
Well, we'll just see.
Lots of people depend on it. Well, I would like to thank Phil and all the morning speakers for their contributions. And then I see that lunch is ready, and we can continue discussion over lunch. Thanks again.